Hello, my name is Ulrik Stridsman. One of my roles is being part of the NSO architect support team. For the last 2 years, I've been putting a lot of focus into measuring performance, scalability, concurrency of NSO as a result of input we get from our customers. In this presentation, I will try to dig into how you can actually benchmark things yourself. Besides just talking about NSO, I also thought I should talk about something different. For this talk, I selected Python Asynchronous I as something that I have discovered to be very, very useful. So I hope I can achieve my goal to sell it into you as well. During developer days last year, you might have seen this slide where we claim that with NSO 6 you can gain a performance increase of 9 times compared to NSO 5. During this presentation I will try to dig into these numbers a little bit, trying to show you what factors that matters when it comes to performance, how we detect that we're, I would say, performing well, but maybe also not performing well. As there are so many factors, it's hard to know what is right and what is wrong. But I will try to do it in an atomic way, doing things in small increments, so we can relate a difference in behavior to that single factor. Part of this presentation, I got to think about what is the meaning of benchmarking. I thought it was just measuring the performance of something and that's it. But it actually also means you should compare with some kind of external criteria. And during this presentation we will compare both with NSO 5, but we will also compare relativity within between the factors that we change when running the tests. I have also realized that there are two statements that have almost the same meaning. There's concurrency and parallelism. Both mean that you're doing things, I would say, at the same time, concurrently. But there's one big distinction. Concurrency means you're doing things at the same time, but not necessarily executing at the same time. Parallelism means you're doing things concurrently, but you also execute them in parallel. And when it comes to computing, that means you need to have multiple cores or multiple systems to achieve this. And during my demo today, I will use CPU utilization as one metrics to know that we do a lot of stuff. I would say both concurrently, but also in parallel. Let's first start with a quick crash course in Python Asynchronous I/O. Let's have a look at this simple program. It starts 100 threads and it executes a number of RESTconf requests. It takes 133 milliseconds to execute, but we do not get any result. I would say this is one of the downsides, I think, by using threads, because you need to encapsulate, create a lot of more code to achieve this. There are other models as well to achieve this, but when I came across Python Asynchronous I/O, I thought, you see, the function looks almost the same, but instead we change our functions into coroutines. We run them as tasks. We wait for them to complete. It goes much faster, and we also get the results. So I would say everything is up, and it it is so easy to use, and this is why I have started to love it. And if we increase the number of concurrent functions, you will see that Python Asynchronous I will outperform even more. In this particular case, it's a factor of 3, and it's still very simplistic programming model, and it's very well suited for network programming, because if you have a computer with one network interface, all the packets will be serialized, so there is no parallelism in network programming. Python Asynchronous I have been around for 20 plus years. It has been, I would say, more or less a wrapper around sockets and the select poll system calls. It was initially implemented in the module named asyncore. It's still available, but with the later version of Python, it has added this syntactic sugar, like the async and await keywords, to make the language easier to use. And it consists of coroutines that you can extrapolate in tasks which are executed in an event loop. And the benefits that I've already mentioned more or less is that you get the concurrent programming model, but with a feeling of sequential programming. It's very easy to gather all the results, but it's also easy to gather the exceptions. As you know, when doing programming, you make mistakes, and you want to know there is something is wrong. So this, I would say, is an important thing. And finally, it's very good performance. How have I used Python Asynchronous I have found it very useful for creating tools, especially those that needs a lot of concurrency. For this demo, I have created a number of tools, but I also, of course, have one exception. That's the CI/SSH Go. I will show the tools during the demo later, but the CI/SSH Go needs, I would say, a separate presentation. It's a very simplistic Cisco iOS CLI device simulator. It's short for Cisco SSH Go. It's implemented in Go, as the name suggests. The benefits: it has very low memory footprint, it's extremely fast, and you can easily simulate tens of thousands of devices in your laptop, so you can very easily exhaust all the TCP ports if you would like to. I want to give a lot of credit to T-Bot New Zealand for this. I've heard it's a NSO user. That's good. But this simulator has been so useful. So I added some extra device support. I did this by taking the Yang modules from our NEDs, used PyYang, and compiled it into the transcript file that describes how the CLI should behave. The low memory footprint is because all devices will return the same config when reading the config, but it has the possibility to also be able to return per device config, but this of course will increase the memory footprint a little bit, but you can still run thousands of devices in your laptop. Okay, now you see this image. I would say it would suggest that what I will do, I will put a lot of stress on NSO, but it's also a suggestion that is what I would like you to do. Okay, let's start the demo. First we will start up some tools that I'm using. I've already started the NSO monitoring stack, and in the configuration file I have added the IP to the running NSO instance. I have an NSO already running. Let's open the dashboard. We can see that it has 1000 devices. It's using the iOS CLI 3.0 example NAD. And it also has 1000 services pre-populated. So we will, during the demo, I will update those services and we will see what kind of throughput we get. I can also show some Grafana dashboards from the monitoring stack. We have, this is the metrics. It shows some number of transactions running, commit queue length, number of sessions. I also have the process monitor that shows processes. I would say metrics for NSO processes. On the left side we have metrics aggregated per package. On the right side we have per process. It can be good for root cause analysis. The monitoring stack is started. Let's also start the device simulator. And now I'm starting and simulating 1000 devices. And you can see how lightning fast it is. It takes less than 1 second to start up and simulate 1000 devices. And I'm running this in my laptop. Okay, to get you some context on how I will push transaction services in this demo. Let's open up. I have organized the pushing of RESTconf calls and transactions in what I call jobs. So this I can start jobs, I can stop jobs, and I can alter parameters of a job to actually change its behavior. Here we can see I have a service intent. I have the input for the service. One is delay, which is synthetic delay in the service to simulate a slow service. Num VLAN is a way to increase the device payload generated by the service, and when it's 0, no device payload will be generated. And these parameters, you can see that delay and data are within these brackets, and those are defined up here. ID is a sequence request. That means it will be increased for each request. Data is a random value to be able to always make changes to services. And we can also see that ID wraps with 1000, so I can push requests and always will be in the limits of the pre-populated services. Okay, let's start. And this will open up a matplotlib window, so we will actually have a graph showing the requests or transactional throughput. I will start up HTOP, so we will all have this view where we can see the CPU utilization and how that is affected by the changes in parameters. And I will start the NSMon, which will include the device simulator. So we will get some memory, CPU, and number of sockets in use by the different processes. We will start one simple job. I will start what's called Python service update, which will update the Python services using atomic transactions. I will set a synthetic delay within the service created to 1000. Let's start without delay. Uh, so now we can actually see this will probably be our first benchmark comparison value. This is how fast we can execute a Python service, create code that does nothing. It just runs and creates some service, some update to CDB. So we will have around 20 transactions per second. I can do show on that job to see what are the current parameters. We can see that concurrency is set to 1, which means all the requests are sequential. Then I can change the parameters. So let's increase the concurrency to 2. Then the question is, how will this affect the throughput? It doesn't seem it affects a lot. Let's set it to 4. No change. Let's set it to 8. So there is not much going on. And since this is a sort of a non-valid use case, it's not, there's no connection to reality. But instead we will set delay to 1000 to simulate that we have also a slow service creator or a slow device behind it. So I will set back the concurrency to 1. I will zoom in, and when it takes 1 second for service create code to run, we can very easily assume that we will get the transaction throughput of 1. Let's increase the concurrency throughput to 2. Now we will see that we will get double the throughput. Now I will increase it even more. I will set it to 16. My laptop has 6 cores, 6 hyper-threading cores, so it's 12 threads running. And that's what you see in the HTOP window in the lower left corner. Let's set it to 16 and see what kind of throughput we get. And this will settle around 12 transactions per second. And what you see now is the reason why we have this performance increase in NSO 6 compared to NSO 5. And this is more or less the reason why we can claim that we have up to 9 times the performance. But there are a lot of different use cases, so not completely easy to actually relate why we in this case have 12 but we say 9 in the slides. Okay, so now we have the first metric to compare to. Now we will start to actually add more realistic more realistic use case. So we'll set delay to 0, but we will set num VLAN to 1. So we will start pushing config to devices. Let's click on the device emulator. Now we can see there's a lot of things happening. We are pushing config to devices. We can also see in the NSMon that we have around 93 open connections towards the simulator. Now it's increased to 118. Now we can see that we are getting a throughput around 4 to 5 transactions per second. Let's show job Python service up. Yeah, now we still have the concurrency level set to 16. So I will decrease that to 1. And now we'll actually see that it only decreases just a little bit. So I would say for this particular use case, there is no use of pushing too many concurrent transactions. Let's increase the concurrency to 2, and then we would be back to around 5 transactions per second. Since we're running atomic transactions, I would say 2 is probably the most effective concurrency to use, because as soon as one transaction is completed, the other one can start up. It's ready. Then the question is, what can we do to add more reality to this test? Since the simulator is so fast, let's stop it. Let's add simulate latency when pushing config to devices. So I will add the 5-second delay for the device to receive the configuration and accept it. Let's go back. Now we can see that we got an orange line in this graph, and that is blue is transactions that are or requests that are successful. Orange is requests that fail. I will set back concurrency to 1. Now I will zoom in a lot so we can actually see what throughput we get. And as expected, when it takes 5 seconds for the device to accept the config, we will get the throughput around 0.2 transactions per second. Let's increase the throughput or the concurrency. Let's set it to 16 and see how that will affect the throughput. Now we see that we don't get that much increase in the throughput. I would say we get nothing. And then the question is, what can we do to get better throughput? And this is actually the single reason why you should start using commit queues. So let's do that. I will stop this job and I will start I would say the same or a similar job, but pushing configuration using commit queues. I'll do show on that job, but we need to set job non-VLAN to 1 because we want config to be pushed to the devices. Now we'll have some lag until the new metrics start to arrive. The reason is because if you started a transaction using RESTconf, if that RESTconf is interrupted, the transactions will still be running, and pushing new transactions will just be blocking until those already started have completed. So it will take a few seconds. Let's show this job again. So see, we have concurrency set to 1, delay is 0, non-VLAN is 1, so we'll push 1 VLAN to each device. And since for the last job I had concurrency set to 16, had concurrency set to 16, and we were running atomic transactions, it would actually be 16 running transactions, and each transaction would take 5 seconds because we have this delay in the simulator. But now we're back on track. So now we still see when we're running transactions using commit queues, but with a concurrency level of 1, we will get the same as using running transactions, atomic transactions. So okay, let's increase the concurrency. What will happen if I set it to 2? I will zoom out a little bit, set it to 15. Now we can see we get double the throughput. I will go even further. I will set it to 8. Okay, seems good. Seems we get around, I'll say, 2 transactions per second. But now I will increase it, I'll say, a lot more. I will set 20. But I will also start another tool to actually visualize the commit queue. So I just created this very simplistic commit queue monitor script using, of course, asyncio. So here we can actually see the size of the commit queue. We can see that we have 8 executing commit queues. And one metric that I found very useful is actually the length of the commit queue. And if you push 8 concurrent transactions and the commit queue length is 8, that means you can probably push a little, push even more concurrent transactions. I will increase it to 20. And when I say you can push more, so you can probably push more concurrent transaction, and we will also gain better throughput. So I increase it to 20. We can see the commit queue length increased to 20. Okay, let's set it to 40. The question is, will NSO be able to keep up and keep a length of 40? Yes, it's possible. And I will set it to 80. Now we can actually see that now it is almost capable of reaching 80, but not completely. Let this run for a few seconds and see what throughput we will end up around. And we can see it settles around 12 transactions per second. And when I say transaction, it means the full cycle from pushing this pushing the service intent and when the config has reached the device. Because with commit you can push service intent very fast into NSO, but then it takes some time for NSO to execute that and push the config. But I would say 12 is the sustained throughput using commit queues for this particular setup. And if you remember, we started with the concurrency of 1 with the throughput of 0.2. Now we have a concurrency of 80 and we have a throughput of 12. That means we have a 60 times increase in throughput, which is, I would say, is great. And this is the single reason why you should start using commit queues. And also one takeaway is have a look at the commit queue length so that you have some metrics to know how fast is the optimal way of pushing transactions into NSO. And just to show you, I will increase the concurrency to 200. Now we should have a look at the CPU utilization. Okay, restart NSS-mon. Now we can see we have a utilization of 325% for NCS, 385. But let's see what happens when we set it to 200. First I will go to the monitoring stack. So now we can see we have the sustained CPU utilization of the let's filter out the NSS process around almost 400%. Let's go back, set it to 200. If we now look at the CPU utilization, we can see the CPU utilization increases, but we also see that the throughput actually goes down. We can see the commit queue length decreases. And since there's so big difference between the number of concurrent requests we're pushing and the commit queue lengths, I would say it's much better to decrease the concurrency level. Let's go back to the monitoring stack, and now we can actually see that we have a big we have an increase in the CPU utilization. We can go to the metrics, and at the same time, if we could have both those graphs in the same dashboard, we can probably quite easily correlate. We can also see this decrease in the commit queue length, and those are the metrics you can have a look at when to actually know if you're pushing the correct number of concurrent transactions towards NSO. I think we're running out of time. Thank you for watching this demo, and welcome back. See you later. As a result of this, I would like to give you some homework. Go home, run a lot of tests, try to push NSO over the edge, pay attention to metrics, how NSO behaves, create a lot of tools, make things reusable, and make versatile test suites, and maybe the most important, let us know. The code I've been using for this demo can be found here. There you also have reference to other related tools. Thank you. That was all for today. See you later.